This animation shows two different approaches to filtering a dataset. On the left, a system extracts the data it wants and deposits it into a pristine, separate container. On the right, the system actively destroys unwanted items, forcing the rest of the sequence to snap forward and fill the gap. These physical mechanisms map perfectly to the two primary programming patterns required for your assignments. The left is the accumulator pattern, which builds data safely. The right is in-place modification, which alters the original data structure directly. If you were coding outside a classroom, you would handle these operations using built-in Python shortcuts. But in CS 109 and 112, importing external tools, string indexing, and list slicing are strictly banned. Relying on built-in methods skips the actual problem-solving step. Writing the raw logic to process these arrays manually is what builds your algorithmic intuition. This diagram maps out the exact data structure for the affordable products assignment. It is a single list, alternating between product names as strings and their prices as floats. To find affordable items, we must build a brand new list from this raw data. The most common logic trap when building a new list is variable scope. If you declare your empty container inside the iteration block, the loop aggressively erases your saved progress on every single cycle. You correct this by moving the initialization step before the loop begins. The container now persists in memory, ready to safely accumulate data across multiple iterations. Because the data alternates, we use a stepped range to jump by 2. We read the string at index I, check the float price at index I plus 1 against our budget, and if it passes, we append both items to our external list. The accumulator pattern is highly reliable. The original data sequence remains completely frozen in place while the loop evaluates it, eliminating the risk of skipping an item. This array tracks a standard for loop, but this time we have to delete data directly from the source list. Watch what happens to the internal mechanics when we target the number 10. Invoking the remove method destroys the data, but it also instantly drags every subsequent element one position to the left to close the gap. A standard for loop blindly advances its internal counter immediately after that shift. The pointer steps to index 2, and the number 15 completely dodges the evaluation phase. In professional environments, programmers bypass this by iterating over a copied slice of the list. Since list slicing is banned in this course, using a for loop to delete items will silently corrupt your data. We need a different structure entirely. This block of code outlines the ICU framework. To safely navigate a collapsing list, we discard the for loop and use a while loop, granting us total manual control over the iteration pointer. We initialize our index variable I at 0. For our control condition, we instruct a loop to run as long as I is less than the total length of the list, allowing the boundary to shrink dynamically as items are removed. Here is the logic puzzle. If the applicant's score triggers the remove method and shifts the entire sequence left, how do we update the index variable to ensure the next item isn't skipped? The index variable remains completely static during a deletion. Because the next unchecked item just slid into the current slot, the pointer stays put. We only increment I inside the else block when an applicant is kept and we safely need to step forward. By isolating the index update inside a conditional branch, the ICU framework prevents the loop from blindly marching past shifting data. This image displays a properly formatted submission. The course grading rubric assigns significant points to dense inline documentation and demands the honor code block sits at the very top of the file. The syntax you write instructs the computer to execute a task. Your inline comments prove to the grader that you actually understand the logic dictating those instructions. This split-screen cheat sheet compares our two blueprints. When building safe new data, initialize an empty container outside a for loop and use append. When modifying raw lists in place, rely on a while loop, the remove method, and a carefully isolated index update. Applying these two exact patterns ensures your code successfully processes data without running afoul of the syllabus constraints. Keep your logic tight, map loops before you type, and document every step.